thank you very much. I suggest we move to the next speaker. Robert Baldemair. He received his diploma and doctorate degree from the Vienna University, and he's from Ericsson, where he has taken different roles in research and standardization, first from digital subscriber line technology, and later working on focusing on the research and development of radio access technologies, of LTE and future radio access technologies. He has received the Ericsson Inventor of the Year 2010 award, and he has a substantial number of contributions to Ericsson patent portfolio.
Is this on? Yeah, I think so. In my presentation, I will give a possible picture of how radio access may look like in 2020, and that is, of course, it's a long time frame, and therefore there's a big how it may look like. First, I will talk shortly about how we believe that radio access in 2020 and LTE will relate to each other. Then I will discuss a little bit challenges of the future and technology components that can address these challenges. And then based on these technology components, I will briefly go into a few scenarios. In the mobile industry, we are used to talk about generations. We had GSM, 2G, wideband CDMA, HSPA, 3G, and now we're in the era of 4G with LTE and LTE Advanced. And the characteristic of each generation is that in principle it could replace each previous generation. So far this didn't really happen. 3G did not yet replace 2G, and 4G certainly did not yet replace 4G. But now from 2010 on or 2011 on, to where do we go from now? Do we see for 2020 more or less still only LTE, but an evolved LTE, let's say LTE++, with, of course, increased performance, but also with extended capabilities to cover new use cases and scenarios? Or do we see really a 5G system, something that could, in the long run, replace LTE 4G? Or is it a complement to an evolution of LTE, and this complement specifically targets new use cases and scenarios? And we believe actually that a combination of an evolution of LTE and dedicated new radio access technologies is the most likely scenario. The reason for that is we believe LTE is quite good for the scenarios it has been designed, and we don't think that there is any kind of magic on the horizon that could more or less make a completely new system much, much better than LTE. And small improvements that are possible definitely will go into the evolution of LTE, and LTE is certainly also capable of extending into new areas. However, there may be some scenarios that are so far away from LTE that if we would try to solve this with LTE, we would end up in a very bad compromise. So then we would more or less jeopardize the LTE performance, but also this new scenario. Therefore, we believe there is for some scenarios potentially room for a new radio access technology. Now, what are the challenges of the future we foresee? First is traffic increase. Right now, we are observing traffic increase of approximately a factor of 2 every year, and there are several independent forecasts predicting, starting from 2010 to 2020, and traffic increase of between 500 and 1,000. This traffic increase is two-folded. First, we have the geographical growth. That is that new areas that do not yet have mobile broadband will get mobile broadband, but that is actually the smaller part of this growth. The bigger part is per user growth, which is driven by that users upgrade from low-end devices to high-end devices. In the past, we had feature phones. Now we have smartphones. In the future, we will have tablets. But then also within a given device class, performance increases. If you take, for example, tablets, they're rather new. The display resolution is not yet overly exciting on these devices, but we can expect that next generation of tablets will have much higher display resolutions. And if you consume video on these high-end devices, probably we would like that the video actually matches our device capabilities. And we should also not forget that we are actually talking about 2020 and beyond. and we should not already reach in the year 2020 the capacity limits of our networks. Therefore, if we talk about 2020 and beyond, then we must be even capable of handle traffic increases larger than this predicted 500 to 1,000. Then what kind of data rates are needed in the future? Sometimes we say a little bit sloppy, 4G is 1 gigabit per second, then we typically have this factor of 10 between generation, so 5G is 10 gigabits per second. But does this really make sense? Is this not a little bit oversimplified? Therefore, we looked a little bit into different scenarios, what kind of data rate is needed in which scenario. And the first scenario we named real-time scenario. That is about consumption of real-time traffic, for example, watching a high-definition video conferencing. And in this case, the human brain is the end receiver, and the reception ability of the human brain is less than 100 megabits per second. Therefore, for this kind of application, we actually do not need more than 100 megabits per second. Probably we can even do with less than that. Then the second scenario is what we call infostation scenario. An infostation is a small local area with extremely high data rates where user, based on prediction, try to download content from the internet and cache it in the terminals so that later when they need it, they do not have to more or less use the umbrella network, they already have it cached in their terminals. In this case, there is in principle no upper limit on the data rate. The higher, the better. And the last scenario is the local processing scenario. Here, information set 1 is stored on the first node. Another set of information is stored on a second node. That could be, for example, picture information stored on a terminal and map information stored in the network. And on the terminal now, we would like not to process this picture information, but actually would like to combine it with the map information. So in this case, it is actually the device, a machine, who does the processing. Therefore, in this case, in principle, there's also no upper limit on the required data rate. From this point, it is similar to infostations, but maybe actually we would like to have this kind of possibility over a wider area, not only over local download zones. So the conclusion from this slide is that higher data rates are important, but one really has to understand when, where, and why certain data rates are needed. In the future, we will also see new traffic types. In the past, the traffic in mobile networks were dominated by voice traffic. Today, it is human-centric mobile broadband traffic. And in the future, in principle, everything that will communicate with each other. Every device, in principle, will be connected. And given the wide application that we have to serve, it is not surprisingly that we will see a very wide variation of device characteristics, but also of traffic characteristics. So if we talk about machine-type communication, some devices have to be of very low cost. For some other devices, the latency is extremely important. For other devices, it is important that the service is very reliable. Other devices will create a very small amount of data, but maybe there are very many of these devices. Then for other devices, energy consumption is very important. So we see there are a very wide range of requirements and device characteristics. And the challenge of future radio access is now to define solutions that actually can fulfill all of these requirements. Then energy efficiency. Today, energy efficiency of a mobile network constitutes around 20 to 35% of the OPEX of a wireless operator. And we also see a trend of densification in wireless networks, also hinting that we have to become more energy efficient. Besides financial reasons, energy efficient networks also opens up for completely new deployment scenarios. Imagine, for example, a solar-powered relay. That's very interesting for a developing country. You can put more or less a relay where you need it. You are not bound to places where you have electrical grid or you don't need diesel generators. And you're also, since it is a relay, you receive your data wirelessly. There's no need for a fiber connection or a copper connection. And also customer requirements or limits set by the government actually can even have an impact on the allowed energy consumption. With that, I will come now to technology components, and they have to be seen neutral. So they can be both applied more or less to evolutions of LTE and also of these potential new radio access technologies. What we see here that should depict a macro cell, and what we are observing right now in our networks is densification. Either we make macro cells more denser and or complement them also with a heterogeneous layer. What we mean by densification, that is extreme densification, so that together with beamforming, that we actually can leave the interference limited regime and actually become noise limited. The reason for that is, if we are so dense, radio links becomes very short and also very often line of sight, which is fundamentally very good for very energy efficient transmissions. Of course, we have now a lot of access nodes in the network, and then of course it's very important that we design good standby procedures into the network, since otherwise this increased power efficiency on the link transmission is eaten up by nodes that are not needed. And since we have so many nodes are probably not always needed, and they should be in a deep sleep mode. And another advantage is, because of the lower output powers, we actually gain access to new spectrum bands that was not possible in the past. Access to alternative spectrum. In theory, it is possible to provide gigabits per second transmission over rather limited bandwidth. However, this becomes very energy inefficient. If we look at this picture here at the bottom of the figure, on the y-axis we have the required energy per bit over the noise density, and on the x-axis we have data rate normalized by bandwidth. The blue vertical line is at 1, meaning that data rates in bits per second is equal to the bandwidth in hertz. For example, if we would like to transmit 1 gigabit per second over 1 gigahertz, that would reflect this blue line, then I'm quite energy efficient. Increasing the bandwidth, that is going on the red curve to the left, gain me a little bit, but not very much. If I go, however, to the right, that is, I reduce the bandwidth, I become very quickly very energy inefficient. This slide or this plot is a little bit pessimistic. It does not take into account MIMO. So if you, for example, take into account MIMO, ideal MIMO with 10 layers, just that is easy, then this blue line would correspond 10 gigabits per second at 1 gigahertz. So the takeaway from this slide is power efficient multi-gigabit per second transmission requires at least several hundreds of megahertz transmission bandwidth. However, it might be very difficult actually to find operator-dedicated spectrum of several hundred megahertz, and it also may become very underutilized. As we said in the discussion on the data rates, multi-gigabits per second transmission are probably not required everywhere. And this spectrum of several hundred of megahertz is probably mainly driven by these extreme data rates. So it is actually not really attractive for an operator either to have licensed spectrum over a whole nation of several hundred megahertz, because it's really not needed everywhere. Therefore, we need some strategies how to solve this spectrum issue. And one possibility, for example, can be operation in unlicensed bands. Here, I think especially the millimeter wave bands and 60 gigahertz can be interesting. Access to secondary spectrum, that was already said before, and also spectrum sharing among operators. It is, however, important to point out we still believe that dedicated spectrum is a very important asset of an operator, and that should be still the baseline. But these above strategies can be used to complement the spectrum holdings of an operator in area where additional spectrum is needed. As we said before, because of the lower power, we gain access to new spectrum bands. And in principle, we are interested in everything from 3 to 300 gigahertz, but I think especially the millimeter wave bands, and here's an example, the 60 gigahertz band seems to be very interesting. Just in the 60 gigahertz band, there is around 7 gigahertz of free unlicensed spectrum available, and most of the spectrum is even available on a worldwide basis. And last but not least, at these very high frequencies, antennas become very small. So massive antenna deployments actually are suddenly possible with a reasonable form factor. When it comes to multi-antenna techniques, if we really go this kind of extreme densification step towards a noise-limited scenario, then probably coordination a la classical comp is probably less important. It becomes more of an optimization, since comp is mainly addressing interference. In the millimeter wave band, we believe that high order beamforming is very important, since we can do it because the antenna solutions are rather small, and it enables spatial isolation. One drawback of the millimeter waves is that they're actually absorbed by the human body. So if someone steps more or less into the transmission link, then the transmission is interrupted. Therefore, for diversity, it is important actually to be able to fast switch of transmission and reception points. At lower frequencies, where this high order beamforming is less practical since the antennas are more bulky, their comp is probably still important to mitigate interference. More advanced schemes, for example, interference alignment, are probably interesting, but it's too early really to say. I mean, academia just started to work on them, so there's more research work needed to really see how they fit in real networks, how they perform in real networks. Device-to-device communication. I would like to talk a little bit about the motivation. Why could that be interesting? The first reason could be offload of cellular communication. So normally a mobile phone talks to the base station talks to another mobile phone. But if two terminals are close to each other, why should we go via this potentially long two-hop way if we actually can go via this short direct link? But it's of course very interesting and important to understand how often such a scenario really happens, that two terminals are close to each other. This comes in two flavors, network-assisted and non-network-assisted. In case of network-assisted, the network actually can help the terminal to find out who are your neighbors and also help in enabling to set up the communication phase. In non-network-assisted, it's up to the terminals to figure out who are your neighbors and also to establish the communication link. Another reason for device-to-device communication could be increased reliability and coverage. For example, national security and public safety. In areas where there is no direct connection with a base station, we could, via other devices, build up a multi-hop connection so that actually areas that are without base station coverage are suddenly connected via this multi-hop connection with the base station. One possible extension to that would be even infrastructure-less operation, especially interesting for national security and public safety again. Yet another area could be, or a motivation for device-to-device communication is if data are only interested in a local area. Imagine, for example, traffic safety-related applications where two cars approach a crossing and the two cars start to communicate with each other to make sure that there is no accident going to happen. In this case, of course, this information is only of interest locally around this crossing. And another example is, for example, wireless headphones, as shown on the right side hand here. With that, I conclude now the technology components and will now discuss a few scenarios that apply some of these technology components. And first, we have super dense networks, which is a little bit more about the densification concept. There is no doubt that in order to meet future traffic and data rate demands, we have to densify our networks. But here we really go further than that. We really look into networks that are magnitudes of order denser than any cellular network of today. And in areas where a super dense network would be built out, the node density, the access node density, can actually become the same as the terminal density. In order for this vision to work, of course, access nodes have to become very cheap. they have to be small, and it must be also very easy to install the network, because otherwise that doesn't work. What are the motivations? Why do we actually want to do that? We would like to move the user closer to the fiber. First of all, that's also related to energy efficiency, since the wireless link is the most energy-consuming link. And then also we would like to give a user the same user experience, independent if he's connected to the fiber or via wireless. As already said, we gain access to new spectrum, and if we design the system in a smart way so that we can send unused access nodes into deep sleep mode, then we also lower the total energy footprint. Such a super dense network, it is unrealistic to believe that it would be built out to provide global or wide area coverage. So super dense networks would always operate under an umbrella network, which is typically 3G or 4G. Therefore, interworking with this umbrella network is very important. And like in heterogeneous networks, the super dense network more or less should absorb all the traffic that is within its area to offload the umbrella network, so that the resources in the umbrella network are freed so that it can serve users outside the super dense coverage in a better way. And deployments we envision are mainly indoor, but also high traffic outdoor environments. And very important component of super dense networks is the wireless backhaul, since it is unrealistic to believe that we would have fiber to every access node. But again, in the millimeter waves, there's large bandwidth available, and with massive antenna deployments, we actually can also make high order beamforming. Another scenario is then machine type communication, which comes in different flavors. First, we have multitude of sensors, which is often connected to this billion of devices scenarios. And here, very often, the sensors have to be of low power and low complexity. A completely different scenarios is industrial control and protection of critical infrastructure. Here, the focus is on high reliability. And it is very important that this network, so meaning the communication between, in this example, the access node and the robot arms, works even if more or less connectivity with the core network is lost. And also most of the communication that is actually ongoing is only of interest locally to this network. And to increase reliability, we believe it is probably dedicated spectrum such networks should operate in. And to increase it even further, we can consider device-to-device multi-hop or mesh topologies. And my last use case for machine type communication is vehicular communication. We already see today that 3G and 4G access comes to the car because of infotainment, which is a mixture of entertainment and information for the driver. But certain traffic safety-related applications might have so tight latency requirements that it's actually not possible to go via the core network. In these cases, either a device-to-device communication could be of interest, or that data are sent to the base station, but from there never sent into the core network, but actually locally forwarded directly at the base station back to the other car. And also here we believe dedicated spectrum is important. With that, I come to my last slide. And to summarize, we believe that future radio access is a range of radio access solutions enabling access to information and sharing of data anywhere and anytime to anyone and anything. Thank you very much.
Thank you very much, Robert, for your presentation. There is space for a couple of questions before we move to the discussion section. Any question on the floor?
I have one question. When you talk about using high frequency band, because we have a lot of capacity there, majority of our traffic is indoor. So if you move to non-line of sight, is that really useful in the sense I can have a huge amount of capacity outside, but if I have not inside, where my traffic is?
But I think especially super dense networks are mainly targeting indoor. So outdoor, dense outdoors maybe as well, but the main application is actually indoor. And we actually believe one access node per room, or even if it is a large room, more than that. So there you would typically have line-of-sight connections.
So when you are saying densification, is densification in each building, in each room, in each floor?
Yes, potentially. I would really see it a little bit like, I mean, that's maybe a little bit of far-fetched vision, but compare it to the electricity. 100 years ago, or maybe 200, I don't know, nobody had electricity. Then electricity came to the house, and now you have in every room 10 wall outlets, but you actually don't need all of them. So why not in the future actually enable the same vision for wireless access as well? You have it really everywhere you need.
Yann Grenenberger, Telefonica IMSD researcher. One question regarding the other spectrum usage. In the light of the recent event with the LTE deployment of Light Squared in US, and with the problem with the GPS interference and everything, do you have any strategy to avoid this with the spectrum you have envisioned for this future radio access deployment? Thanks.
I think when it is, for example, unlicensed spectrum, then probably this is the first technology that goes in there that probably determines the strategies we have to use. If we should, for example, go into the 5 gigahertz wireless LAN network, then even through by regulation, I think there is no real rule that states how we should behave. If we would behave in an improper way, then probably regulation would come and kick us out. Therefore, if we would like to go with LTE, for example, into the 5 gigahertz band, which is dominated by wireless LAN, then LTE would probably have to adopt to wireless LAN. If it is a completely new area, then probably one should actually try to really get an agreement across technology how fair sharing should be achieved. And if it is, for example, secondary spectrum access in TV or radar bands, then I guess, I mean, the first priority is, of course, protecting the primary user, which probably is reducing power and not using those bands where these bands are not wide.
Any more questions from the floor? I have another question before we move to the panel session. You mentioned, and you have been talking about active antennas and beamforming as a way of making noise-limited scenario instead of interference-limited. We fully agree from Telefonica that antennas are a key element for the future of networks. We need to have better control on the radiation patterns. But when we talk about, for example, adding active elements to have beamforming and advanced antenna solutions, we have the issue or the problem of all the legacy networks. I mean, when you go to a site, in our case, and every operator case, you will have many antennas covering many different frequency bands, GSM, 3G, multi-operator. We are thinking now on 8 ports, 10 ports antennas for standard rollout. We are convinced about the need of the active antennas, but we see a lot of issues in terms of infrastructure to really make it happen, combine it with all the legacy networks we have at the moment in the field. So what is your view about how this should evolve towards really being taking the benefits of active antennas with these limitations in terms of infrastructure?
That's a little bit out of my area, but I believe in this area, self-organizing network is very important. You really have to have measurement procedures in place that actually can measure certain quantities in the network, and then you, to be able to more or less automatically adapt the adaptive antenna to what is best right now. For example, if you would like to switch off certain nodes, as we have heard before, active antennas can be used. You could increase, for example, the tilt a little bit, that you increase the cell coverage, that you can jump in for other network nodes that are now in sleep mode. But in order to do that in an automatic fashion, I think SON is very important and robust procedures that really protect the network performance.
Thank you very much, Robert.
Thank you.
I suggest we move to the last part of the panel.